My name is Robert Bassey. I'm with the FAA's Office of Airport Engineering. I would love to have been here today, but due to a schedule conflict with another meeting, I am providing this pre-recorded presentation. My goal today is to provide an update on our vertiport design standards development process at the FAA, as well as provide you an insight into the update that's pending to Engineering Brief 105 for vertiport design. So since 2019, the FAA has essentially embarked on a multi-year research project to develop vertiport design standards. That project culminated in September 2022 in the release of Engineering Brief 105. That engineering brief provided specific guidance for public and private vertiports and vertistops, including how to modify existing helicopter and airplane landing facilities to vertiport standards and the establishment of new vertiport sites. That EB focused on VFR operations with a pilot on board, lower operational tempo, and VTOL aircraft with electric propulsion that had all the characteristics and performance capabilities of a reference aircraft that we detailed in that engineering brief. We do plan to update that engineering brief by the end of this calendar year in accordance with the results of recently completed operational testing. That EB update is scheduled to be released for industry comment by the end of this week, which is September 20th, 2024. So given the rapidly changing AAM landscape and the varying aircraft design and performance capabilities, the FAA also plans to publish an AC or advisory circular for vertiport design by the end of calendar year 2025. That AC will fully transition from a prescriptive or compliance-based standard to what will be more of a performance-based standard. That would involve defining VTOLs into various performance classes as an appropriate consideration in setting vertiport design standards. We would essentially have categories of facilities that require different design criteria based on the design characteristics and performance capabilities of the differing VTOL aircraft groups. Once again, that would involve categorization of these aircraft. We will do that based on their performance capabilities, based on their size, based on aerodynamic issues we've identified, the weight of these aircraft, and other parameters. Any identified susceptibilities we would need to account for with an appropriate risk mitigation strategy, either through operational limitations or through infrastructure design. Then subsequently, these landing facilities will need to be classified also by not just only the types of aircraft that use the facility, but also the type of services that will be provided at that facility, as well as the operational and dimensional characteristics of that critical design aircraft. This is all to ensure that these landing facilities are appropriately sized and have a margin of safety between allowable obstructions and the required aircraft performance. So what will this AC include in detail? It will also address autonomy, in addition to what's already included in the EB. It will address different propulsion methods. It will address alternative fuel sources. We will start to look at higher tempo facilities and also IFR capability. The reasoning here is that these power lift aircraft configurations, their operational specifications and takeoff and approach abilities would in some cases be different from conventional helicopters and in a sense warrants different facility sizing criteria and different design considerations. So to support the development of comprehensive vertiport design AC, additional research is being conducted to garner VTOL aircraft performance data on downwash outwash effects, thermal runway related to the batteries of these aircraft, and also to ensure safe passenger egress in the event of a thermal runway. We're going to look at failure conditions and degradation in performance, landing precision, climb descent gradients for this aircraft, and all azimuth weather capabilities, with the data being used to fill in aircraft information gaps. Now, over the last year, the FAA has conducted small-scale field testing to further research and consider the effects of VTOL aircraft operations as they interact with the TLOF, the FADO, and the safety area. The goal being to use the findings from this testing effort to influence ongoing vertiport design guidance and operational standards, and then create a pathway to less restrictive vertiport design sizing, and also address the FADO load-bearing requirements as that research is completed and the relevant performance data is gleaned. So some of the questions we look to answer by way of this small-scale testing: where does the downwash outwash created by this aircraft, where does that go? How accurately does this aircraft land? What path, glide path, if you will, does this aircraft follow on takeoff and landing? And how well does it maneuver on the ground? So the testing we conducted took place at different OEM flight operations facilities. These aircraft had been identified to represent full-scale aircraft across the varied VTOL aircraft platforms that are currently working towards FAA certification. The objective was to obtain real-world flight data from VTOL aircraft, capturing each of the three current propulsions. That's the vector thrust propulsion, the lifting cruise propulsion, and a multi-copter propulsion, and capture this data doing hover, takeoff, and landing. So specifically to downwash, outwash, what we looked to do here was to measure the velocity and the direction of the downwash, outwash from each VTOL aircraft type across, once again, the fundamental TLOF, fatal, and safety area as it was described in EB 105, and then document that downwash, outwash profile data for each aircraft and try to identify when that downwash, outwash exceeded the safety area with its velocity and direction, and then compare that data to computer modeling that was already done. And by observing the interactions of the VTOL aircraft on vertiports based on our EB 105, as well as our heliport design guidance, using a variety of parameters such as the aircraft weights, the number of rotors, the rotor's height above the ground, the disk loading, and the number of rotors in ground effect versus the rotors that were out of ground effect. The testing system we used looked at all these factors. That system was portable, and it was taken from one OEM facility to another in an effort to ensure consistent data collection across the research methodology. Now, this data was used to inform, once again, the creation of the update to the engineering brief, but it will also inform the creation of the advisory circular. And the goal, once again, is to configure and lay out vertiports, right? So this task will provide some initial guidance on what features from this testing and the correlated models are of most importance to minimizing the adverse impact of the VTOL aircraft downwash and outwash on personnel, property, other aircraft, and surrounding structures. So we also measured the landing scatter. So the landing precision of these aircraft. So the goal here was to measure the landing spots on the TLOF for each VTOL aircraft to determine the distance from the center of the TLOF to the landing gear. So the distance of the TLOF center to the final location of the aircraft landing gear on each landing was marked and surveyed. That landing precision and scatter data was captured via 30 landings from a full approach, and that was the goal, once again, to determine the landing precision of each VTOL aircraft type. Now, this was a test objective that we didn't quite get to actualize doing our operational testing, largely because conforming aircraft was not made available to us by OEMs in order to perform this test. And that continues to be a headwind that we face, is the ability to get conforming aircraft to perform a lot of the tests that we think are requisite to make the modifications to our guidance. All right, so but the goal here was to try to document the approach departure paths for each aircraft and to see if they meet or exceed the existing 821 that exists for helicopters. That's a goal, that's a test objective that we're going to carry on into our next phase of testing to support the development of the advisory circular. Now, likewise, this test here was one that we couldn't actually actualize during our operational testing phase to support the EB update. Now, but the test goal here was to try to measure the turn radius for each VTOL aircraft type in order to determine the tightest turn radius of a wheeled VTOL aircraft from a stop position and how well that aircraft maneuvers on the ground, right? This was not applicable to skid aircraft necessarily. The ground turning radius we would measure across 16 turns on different headings, all beginning once again from a stop position. Now, this is one test effort that, because we're not able to accomplish largely in the current phase of operational testing that was recently completed, for the EB update, we will look to carry over into that next phase of testing that will support the development of the more comprehensive performance-based advisory circular. So here we just try to highlight what's some of these parameters that we try to gather data for as part of the operational testing, what they would influence specifically in the guidance. So the downwash outwash has a direct influence on the sizing of the TLOF based on the safety area. The landing precision, as you will see once that EB update is released, has an influence on the sizing of the TLOF and the load bearing requirements of the FADO. The approach departure profile obviously will influence the slope requirements. That wasn't addressed in the EB update because once again we were not able to capture that relevant data. And then the taxi turn radius would influence the load bearing requirements of the FATO, and we look forward to being able to collect that data once again in that next phase of operational testing. The EB update that's soon to be released for industry review did address the size of the TLOF for certain types of aircraft. Now, before we get into specifically what changes may be coming with respect to TLOF sizing, let's define some key terms. The FATO. What is the FATO? That's the defined area over which the final phase of an approach maneuver is completed to a hover or a landing. And that's also the area from which a takeoff maneuver is commenced. The FATO essentially takes into account errors that are associated with normal maneuvering by the aircraft. Axial turns as an example. The TLOF, that's that hard paved surface within the FATO, and that's used to define the lower limits of navigable airspace for the determination of obstructions to navigable airspace. And that's presumed to be, and those obstructions are presumed to be hazards to air navigation until an FAA airspace study determines otherwise. Now, the safety area, which is the third critical defined area which within a vertiport or a heliport for that matter, is that defined area that surrounds the FATO, which is free of obstacles, other than those that are required for air navigation purposes. The safety area is really intended to reduce the risk of damage to aircraft accidentally diverging from the FATO. As such, as opposed to the FATO, which takes into account errors associated with normal maneuvering, the safety area takes account errors that are associated with abnormal maneuvering, associated with environmental conditions such as strong winds and the like. Now, with respect to TLOF size, you're going to see that in the EB update, for certain types of aircraft, and there's a delineation made in the EB between aircraft that have essentially VTOL capability with more than 2 lift generating propellers with no fixed wing surface for horizontal flight, and those aircraft that essentially have a wing surface and also feature a transitioning phase. We're seeing some performance differences between them, and that's going to kind of dictate the sizing of the TLOF for those different types of aircraft that fit within those categories. So that's what you're getting a glimpse of here, and how we would determine that based on what is the landing distance, the average landing distance, accommodating for some sort of positioning error, and making sure that that aircraft encompasses all the propulsion units and wheels of the aircraft that the TLOF is being designed for. So key takeaway here is a specification around TLOF size and a differentiation between aircraft that are winged and feature a transitioning phase in terms of performance and landing precision, and aircraft that don't have a fixed wing surface and do not necessarily feature a transitioning phase. So related to the delineation between aircraft without a fixed wing surface and aircraft with a fixed wing surface featuring or not featuring a transitioning phase is this idea of effective translational lift, or ETL as it's also known. This is what is required for most traditional helicopters to fly. That is essentially to hover in ground effect, to accelerate forward and then climb, which also provides for, in vertiport design or heliport design, an increased safety margin and a minimum acceleration distance in order to provide the pilot with a longer takeoff length for liftoff within ground effect. Once again, this is essentially to accelerate forward before getting altitude and taking advantage of ground effect. Unlike traditional helicopters, what we're noticing is that these emerging aircraft do not necessarily require ETL to fly. As such, it is debatable if the increased safety margin and minimum acceleration distance is needed by these aircraft. This will then impact the sizing and geometry of the safety critical areas such as the TLOF and the FATO. So the EB update addresses this sizing and geometry issue as it relates to ETL for certain aircraft types, and the possibility that the FATO is made contiguous and flush with the TLOF. Related to that, what you're seeing here is also the smallest enclosing circle of the propellers based on different types of aircraft designs, which will obviously dictate the size of the TLOF if the idea is that the TLOF enclose all the propulsion units and wheels of the aircraft. So once again, that minimum enclosing circle that you saw in that last slide is really going to serve as that controlling dimension or that parameter which is going to standardize the approach to sizing vertiports on the basis of the largest overall dimension, which will not necessarily, as shown on that last slide again, encompass the entire defined area of the aircraft. So if we apply that, essentially for certain types of aircraft, once again, not one size fits all, because this is going to be a performance-based standard, and especially as it evolves into the advisory circular. But for certain types of aircraft in the engineering brief revision, you're going to see the size all the way to the left of your heliport or your GA hospital heliport juxtaposed against the size of a vertiport that existed in the initial draft or the initial version of the engineering brief 105. And then for a certain type of aircraft in the EB update, or 105A as we're calling it, this is with the sizing and geometry for that certain type of aircraft that will be highlighted in the EB update. So what is our overarching approach at the FAA? We are focused on using a data-driven approach to ensure that AAM infrastructure standards allow for safe operations. And then we're going to do that by way of performance-based guidance. So the engineering brief that we initially issued was prescriptive and compliance-based, but the update will transition or begin the transition to performance-based standards, and that will be by the end of this calendar year. We're going to follow that on once again with a performance-based vertiport design AC by the end of calendar year 2025, and there will be a series of internal guidance and communications that will continue to be released by the FAA along the same lines. The heliport design guidance we recognize is prescriptive, and that's limited primarily to heliports and helicopter operations. We're also going to try to transition that guidance over the next several years to a performance-based standard that will require rulemaking, extensive industry engagement, and gathering and gleaning performance data for helicopters. The goal over time is to settle on a holistic vertical flight infrastructure guidance document that is performance-based and encompasses vertiport and heliport design into one document.